Welcome to solverfy.
6.19. So we'd like to use the binomial expansion to show that this is an approximation for the change in the acceleration due to gravity with change as you increase your distance from the surface of the Earth by amounts that are small compared to the Earth's radius. We want to explain what the minus sign in this means, and we want to use this to compute little g for a distance 125 kilometers above the Earth's surface, and then compare that to directly using Newton's law of gravitation. So first, g plus delta g is going to be equal to the gravitational constant times the mass of the Earth divided by the radius of the Earth plus the change in r we're making. So far this is exact. Now it will be helpful if we write this slightly differently. So if we take out an RE squared from that, we have 1 plus delta R over RE squared and then rewriting this so it's easier to apply the binomial expansion. We have the value of little g at Earth's surface times 1 plus the ratio of the change in distance to the Earth's radius to the negative second power Now, applying the binomial expansion, we know that we have 1 plus or minus x to the n is equal to 1 plus or minus nx plus n times n minus 1 over 2 x squared, etc. And so just keeping the first two terms in this, because we can see here we already want a linear approximation, so we only need to keep the linear term here. Right, we have g times 1 plus nx, n is negative 2, so we get minus 2, and then x is delta r over re. So from this, we can see that delta g, so this is g plus delta g, and so if we subtract g off from both sides, we're just left with delta g equals negative 2g times delta r over re, which is what we wanted. Now the reason that this is negative is because the acceleration due to gravity decreases as your distance from the center of the gravitating object increases, because it's an inverse square sort of thing. So as r goes up, g has to go down. Now for part C, we want to look at this for a delta R of 125 kilometers. So we have g plus delta g. It's going to be 9.8 meters per second squared times 1 minus 2 times our 125 kilometers, which is 1.25 times 10 to the 10 to the 5th meters, divided by the radius of the Earth, which is 6.38 times 10 to the 8th meters. And so we get 9.42 meters per second squared. Now, if we calculate this directly using Newton's law of gravitation, we have g times the mass of the Earth divided by your distance squared. So we know the mass of the Earth, we know the gravitational constant. Now we just add these two together instead of dividing them and then square it down here. And so you get 9.43 meters per second squared. And so we see these are actually fairly close to each other, and the difference is only about 1/10 of 1% actually. So for this sort of distance at least, which gets you almost up into like the orbits of many, satellites and the space shuttle and stuff, this actually works quite well.